So network troubleshooting from scratch. The idea for this talk appeared a while ago when I was at a customer site, and I'm not doing that much of network analysis anymore in my personal life. My current profession is doing instant response. So I deal with ransomware attacks a lot and other kind of network intrusions. And whenever that happens, especially with ransomware, you need to help the customer get their systems recovered and running again, which means very often that you have to recover hundreds of servers that were all shut down because of the encryption. And if you start that many servers from a backup or whatever, however you recovered them, very often people find out that they have problems with applications that they didn't expect because the systems were running for such a long time and they're not sure why it's not working anymore. And we will have one example of this in a practical demo. I try to do as much practical stuff as I can, but I also brought more slides than usual. Usually I only have like a handful because the rest is live, but I thought in this case I need to explain a few concepts to you, and this is why I have more slides than usual. All right, so let's get started. Well, I'm Jasper Bongertz. I'm from Germany. I'm working at a company called G-Data Advanced Analytics. I'm the head of the incident response team, and I like to look at packets and share knowledge about troubleshooting. So I'm glad that you're here. A few of you have a lot of experience in troubleshooting, and I know you, so we'll see what happens. All right. The principles of troubleshooting, and that is something that I need to go through because very often, especially if you're new, you might skip a few of those or all of those, and it will hurt you at some point because troubleshooting is something where you need to have a little bit of a discipline, because otherwise you will come to the wrong conclusion or talk to people and tell them you found the problem and then it turned out it was something else entirely. So let's go into them. My laptop is really slow today. I don't know why. First of all, it's do not assume, verify. That is a general thing that you need to do when you're troubleshooting, because very often people tell you, this isn't working. I know it's exactly is this. It is this kind of root cause, and you need to fix this. And very often they have this kind of Google experience. My brother's a doctor, and very often he has patients coming in telling him exactly what they think they have as an illness, because people try to figure things out and without really having the expertise. So it's always good to not assume, but verify. So even if you think, yeah, this is a system running this and that, and I know it's up and running and the software is working, maybe it's better to verify that. And then have a check mark like, yeah, it is working, so I can skip over that part. But never assume something is when you haven't, is working in a way or running in a way or is in a certain state when you haven't checked. The next thing is do not jump to conclusions, because very often it's like we have seen something and it's familiar to something we have seen before, and we say, I know what this is, it is this. And that is something that very often also bites us in the behind, because it turns out to be something else entirely. So it's good to have a couple of ideas what could be the problem, but then again, go to step one. Do not assume, verify. So try to prove it. And the best way to do this is to try to find a way or find a reason why what you're assuming is not correct. So we always try to prove the negative, because that works much better than trying to prove the other way around, because you will try to bend facts to whatever you think you want to have. And it's better to assume something and then try to prove the negative. Choose your tools and approach wisely. I mean, this is the Wireshark conference, so we're all probably used to running Wireshark, or assume that whatever we do in troubleshooting means start up Wireshark, capture packets, do something. And sometimes that's not the case. So Wireshark is like a heavyweight when it comes to troubleshooting. You can do a lot of things with it, but maybe it's not the first tool that you should use, or you should use it in combination with other tools. And I will also show that in my in the demos that I do. Next thing is, if you're implementing a change, do one at a time. I've seen so many people like changing 3 times at once, and then something worked, but they don't know which one it was, or nothing worked and they keep it like as it is and continue to add more things that they change, which is also the next thing. Rollback changes, they weren't successful. So if you need to find a solution to a problem, it's not very good. It's not a good approach to just change a lot of things and then in the end, if it works finally, not knowing what it is. And the one thing we hate, all of us probably, documentation. Document what you're doing as much as possible, because I don't know if it happened to you, but it happens to a lot of us looking at PCAPs a lot. We look at a PCAP that we took like half a year ago and we're like, what was in there? I know there was a problem that I found, and I think it's this problem, but how did I get there? And documentation is really important because it allows you to basically keep in mind what you did and reapply it for the next time that you have a similar problem. So the next thing, Occam's razor, I don't know if I pronounce it correctly because I'm from Germany and English is not my first language. The simplest explanation is usually the correct one. So don't try to find a very obscure cause for your problem. Try to go with the simple ones first. And if they don't turn out to be the correct ones, then you can go into the crazy ones. But go with the simple ones first. Okay, so troubleshooting goals are usually, from my kind of experience, there may be a few more, related to 2 things. The first of them is connection state, which means a connection cannot be established. So you're trying to get an application running and somehow it doesn't work because you cannot get any kind of connection. Or if you have a connection, it breaks down unexpectedly or suddenly is disrupted. Of course, there can be reasons like power outages or like a backhoe destroying a cable or these kind of things, but not always. Very often it's something else that breaks the connection, and we will also take a look at one of those examples. The other thing, and that is something we're not going to look at today that much, is throughput issues. So if a connection is working, but it's not as fast as you want it to be, it could be a couple of things. For example, the available bandwidth is not high enough. That would be an easy one. Where it gets more complicated is if you're tracking down delays caused by distance, because even though electrical signals are quite fast, they're 2/3 of light speed. If you have to cover a distance, let's say from the US to Europe, it will take a couple of milliseconds. And if you're doing a communication where you're going back and forth a lot, like requesting data, getting data, requesting the next kind of data, getting data back, you go back and forth a lot, and that adds up really quick. So it depends on the application type if that's a problem. And then, of course, there's queuing. If one of the links that you're using is very, very heavily loaded with packets, your packets may get put into a queue and delayed. And that is another thing that can really slow down a conversation. Packet loss is, of course, also possible. Packet loss is something that usually happens either in the network or on the 2 systems that are talking to each other. Those are the 3 places in general. Packet loss usually means something is lost because it couldn't be transported in time. So if a packet is in a queue for quite some time and there's more and more packets coming, or the queue is completely full, then it could happen that packets are dropped. and that it would be in the network. You could also have that on a system that you're talking to because it's overloaded. So packet loss usually means that there's some sort of congestion that couldn't be solved by queuing, and that means that packets are lost. All right, so let's take a look at connection state, and I hope that what I did here is also useful for those in the Zoom session, because it's a little animated. I tried to reduce the animation to a minimum so that it doesn't do any fancy fading in, fading out, but we'll see how that works. So I have a couple of examples for what does it take to establish a connection and what can go wrong. The first of all, the very positive example of a successful TCP connection. Who of you doesn't know what the TCP three-way handshake is? Anyone? You don't? Okay, so any TCP connection that needs to be established or wants to be established has to exchange a kind of handshake first, which means one system is telling the other system, hey, I want to talk to you, which is a synchronized packet or a SYN packet. This is the one you see here. The client wants to talk to the server, so it sends a SYN, which means, hey, I want to talk to you. And when the server has a service running on that port that is the SYN sent to, it will reply with a SYN ACK, which means, hey, first of all, I acknowledge that I got your synchronized packet, and I also want to talk to you, which is why I'm sending you a synchronized packet as well. It's both together in one packet, of course. It's only two flags being set. So SYN from the client means, hey, server, I want to talk to you. SYN ACK from the server means, I got your SYN, and I also want to talk to you. And then there's the third packet from the client saying, hey, great, now we have a connection. That's basically the so-called three-way handshake. Both of the parties agreeing that they want to talk to each other, and everything is fine. So this is what you will see in any TCP connection that is established successfully. By the way, the TCP three-way handshake is something some of us could talk like half a day over, like explaining all the options that could be set in there and all the things that can go wrong with it. I'm not going to do that today because I only have about an hour. So let's just assume, okay, this is a successful three-way handshake, and well, it says on the side, it's successful. Now let's take a look at a different example. Once again, the client is sending a SYN. Now the server sends something else back. It sends a reset. Does anyone know what that means? Yeah? Any idea what that means, sending a reset? Louder? It doesn't want to talk, right? Reset means, no, sorry, there's nothing here that could talk to you. So basically, it means there's no service running on that destination port. Yeah, so the operating system will tell you, sorry, there's nothing here. Yeah, so if you're seeing a SYN reset, that means there's a service not running on that port. So troubleshooting that would be, first of all, why do you try to connect to that port on that server? Is there a service supposed to be running on that port? And if you're getting a reset back and you know that there should be a service running, then something is not right on that PC or on that server. Yeah, the service should be running, but it isn't. And you can see that in the network. So that is a good hint of, well, maybe I'm contacting the wrong server and the service is not supposed to be running over there. Then you have the wrong IP address. Or you have the right IP address and the service should be running. Well, then it isn't. And that is something that the server operator needs to fix. Yeah, so this is a very easy thing to diagnose, actually, if you have the packets, of course. Okay, a few of you are still writing things down, so I'll give you a couple moments to do that. The next one, let's see. Once again, we have a SYN. And then nothing happens. And then there's another SYN. That is strange, right? Because usually we want the server to tell us, hey, I want to talk to you too, or sorry, that server is not here. This is kind of like ghosting us. He's not doing anything. So what is that? Why could that happen? Any idea? It could be packet drop, yes, because if the SYN gets lost in transit, it could be that the server never got it. Very good, yes. It could be a firewall, yes. So I basically said in this case, destination port is firewalled, but you're also very correct. It could be lost. So in both cases, that would mean that the client waits a little bit and he tries again. Yeah, so I will have an example later of showing you how that can look if packets get lost in a handshake. That is sometimes quite scary, but yeah, in this case, it's either destination port firewalled or you have a packet loss. I need to add that to the slide later. Good, next one. And to go back to this one, if it's firewalled on the server, because in this case, there's no firewall in between, right? So I have an example with a firewall in between, that is this one. So in this case, the connection goes to the firewall and the firewall says reset. It never reaches the server. And that is a typical firewall setting where you tell the firewall to reject connections, which is something that you shouldn't do for public-facing firewalls, because it tells the bad guys out there that there's a firewall and it's rejecting your packets. So this is called a reject rule in most firewalls that I know. And this is something that, for example, I do only in firewalls that are internally in or running in the internal network, because it accelerates troubleshooting. Yeah, because if you see it's not working, first of all, the reset will arrive very quickly, so the client will know this won't work. And he won't try again, because you have seen what happens if it doesn't say anything, or we will see it now in the next one. The SYN is sent and nothing happens. And another SYN is sent because there was nothing coming back. And that is the firewall with the drop rule, or block, drop, whatever. It basically means don't let it pass and discard the packet without saying anything. Yeah. So that would be that kind of setting that you would have for a internet-facing firewall, dropping everything that is not allowed to go through without giving back anything. Yeah. The problem here for an internal firewall would be that the client is spending a lot of time on trying and trying again, like 3 times usually with the SYNs. And it's always waiting, which means that the user experience is also not good, because he doesn't get a quick feedback that this won't work ever. Yeah, so the client is trying, waiting, trying, waiting, trying, waiting, and then aborting after the 3rd time. But that can be a couple of seconds, and that's frustrating. So for internal firewalls, I often use a reject rule, so it gets rejected quickly, and everybody knows, okay, there's a firewall in between. Yeah. By the way, the same thing works if you're using UDP, because all of this are TCP examples. If you have UDP being sent to a firewall that rejects it, you will get an ICMP packet back telling you administratively prohibited. Yeah, if you do silent drop or dropping the packets without saying anything, well, then there's nothing coming back in both situations. All right, so the other thing that is quite interesting to know from a troubleshooting perspective is the time to live and hop count. If you've never worked with it, I can recommend taking a good look at it, because it's very good, or it's very useful to surprise people with conclusions that they have no idea how you got there, because TTL is a great indication of some network topology. Because I don't know if you know this, but the TTL used to be a second-based thing. So the TTL was assumed to be 1 second per router hop that the packet travels across. If you have seen network communications in the recent times, 1 second would be like ages, and nobody wants to wait 2 seconds. So we are used to waiting microseconds for a router hop, but it's still in the original specification, it's called a second value. So the time to live works like this. Oh, first of all, IPv6, it's called hop count because they found out, well, it's more like a hop count and not a time to live. It's reduced by 1 per hop. So whenever a packet, an IP packet, crosses a router or a router, however you pronounce it, the TTL is reduced by 1. What happens if it hits 0? It's dropped, because then it's been traveling so much in circles probably that it's a good idea to drop it, because otherwise you have this kind of feedback loop where the packets keep traveling in the network and never find a way to go. So this is a mechanism to get packets dropped if they travel in loops. Interesting about this is that there are default stat values, and those are either 64 or 255 for Unix, Linux, BSD OSs. So the packets start with 64 TTL or 255, and 128 for Windows OSs. Yeah, and this is quite useful, because if you're receiving packets, or if you're looking at packets and look at the TTL fields, you can tell how far it traveled to the point of capture, right? Because if you're seeing a packet with a TTL of 120, then you know from the original sender it must have come across 8 hops, 8 routers in between. Yeah, so finding out how far something is away or how many routers are in between is often very useful, and we will see that in the example that I'm going to do soon. We could, for example, do something like this. Let's see. I'm in the come on. Where's my command prompt? I'm in the Wi-Fi here, so the IP address of the Wi-Fi router or default gateway is 172.20.01. And if I ping this, we can see what TTL is coming back, because I don't know if you noticed, but ping will give you the TTL of the answer. And you can see it's coming back with 128, which is not surprising, because I'm pinging my default gateway. And my default gateway is the router in this network that I'm in that allows me to go into the internet or wherever I want to go. The default gateway is always the one that I talk to if I cannot reach a system, or if I want to reach a system that is not in my local network. So of course it has a TTL that is either 64 or 255 or 128. In this case, it's 128, which means it's in the same subnet. Okay, so let's say if we ping google.com, you will see it has a TTL of 112. So we have like 16 hops between us and this, and then this server, which is 16 hops is a little bit, yeah. But maybe you know this, but I think the Google DNS is 8888 quad 8. And DNS is very important, and it needs to be really fast. So it would be good if it would be closer to me than 112 or 14 hops, 16 hops, sorry. So let's see how far that is away from me. And you can see it's at 59. So now I think it's maybe not starting at 128, because that would be very far away. I assume it's at 64, so it's only 5 hops away, which is much better than 16, right? So that is because DNS servers are placed very close to the clients, or clients always try to look for the DNS server that is the closest. And we can tell, yeah, this is closer than the google.com, just by pinging it and looking at the TTL. Yeah, this is a good trick. If somebody asks you like how many firewalls or how many routers are between me and that system, you can just ping it and look at the TTL. And if it says 128, then it's like, yeah, there's nothing. Or if it's 64, then there's nothing. Yeah, but if there's something, it will be 63 or 127. So it's really useful to have this TTL in mind if you need to find out, is there a system in between that I'm not aware of? Because with that, you can figure it out. All right, where's my mouse? There it is. Okay, we already established that if the TTL or hop count reaches 0, the packet is dropped. It can be dropped with or without notification. There are routers on the internet that just drop packets and never tell you, because we would be going into the security field for this kind of thing. You could try to denial of service a router if you're sending a lot of packets that all get dropped by this router and it has to inform you all the time that it got dropped. You can overload the CPU of a router really quickly doing this. So very often they're not telling you this. And if you're using traceroute, for example, to find the path where the packets are traveling, sometimes you see that there's asterisks coming back, like empty lines where there's no timing in there. And that very often is because you are not getting anything back when a packet gets discarded. So just to take a look at it, I have no idea if how the traceroute will work in this case. This will give me timings, so nothing is dropped. This one is dropped. You see an asterisk there, so there was one drop apparently. And whenever you see this star or this asterisk there, it means the packet was dropped without any notification. Good. So, time to live. This is how it works, basically. If you send a SYN, and let's say it's a Windows client, it has a TTL of 128, starting with it. And if there's nothing in between and it arrives at the server, we will see that it still has a TTL of 128. So if we capture on the server and we see something arrive with a TTL of 64, 255, or 128, we know, okay, this came from the local subnet. There was no router in between, especially if you see 255. Why? Because it's the highest number. So it can't have started at 256, because the highest number that you can start it with a byte, and it's a byte value, is 255. So this fact is actually used for security purposes in IPv6, because they're using that kind of thing to make sure that packets stay in the local subnet and cannot leave it. Or no, the other way around. They make sure that packets are from the local subnet and not from the outside. Okay. I need to look at IPv6 more. I haven't in the past or in the recent past that much. Okay, so he's talking back, and since there's nothing in between, we'll see TTL 64 in both directions. Some of us would now go and say, well, the client must be Windows, the server must be a Linux kind of thing, because of 128 being typical for a Windows system and 64 being typical for a Linux system. Yeah, so this is something that you can also use if you know the starting values, where they start. That is quite useful actually to figure out what's going on. Okay, my laptop is really slow right now. So what happens with the firewall in between? Let's assume the packets is allowed to get through. So we send it with TTL 128. What will be the value when it reaches the server? Any idea? Which one? 127, yes, because it has had to cross a router. But basically, a firewall is nothing other than a router with some security, making sure that only allowed packets get through. I could have put a router here. It wouldn't matter. Yeah, so the packet going through a hop, like a firewall or a router, means the TTL gets reduced. So if we would be capturing on the server now, we would know, okay, the other system is still probably a Windows because it's very close to 128. So that would be probably the starting value. And there's one hop between us and the client. Yeah, this is something that you can just tell from looking at the TTL in a packet. And the answer does the same thing. It goes back with 64, it crosses the hop, and it arrives with TT63. Yeah, so also on the client side, if you're capturing on the client side, then you can tell, oh, yeah, the server is one hop away. There's one router, firewall, whatever, between me and that device. And that is very often useful because of what I will show you in the scenario that I have here. Scenario 1, and we are going to look at 2 of them. I don't know what my time is, so how much do I have left? Okay, 35 minutes. Okay, then we will be able to do both, I think, which is good. Evil firewall means I was doing a ransomware case, and in that ransomware case, about 700, 800 servers got encrypted. And we had to restore them from backup and decrypt things sometimes, depending on what was the fastest way to get this running again. And it was a hospital, which meant we needed to get things running as quick as possible again. And in a hospital, very often you have medical systems that are required for all kinds of things. In this case, I think it was something that had to do with the MRI scans or the CT scans or something. They needed to get access to the pictures so that they can use it for surgery. And the guy responsible for that system was telling me it doesn't work. He can't connect to his server. He has a client PC that is running. It doesn't work. He cannot get to the server, and it must be the firewall. So if you remember the beginning of this talk, if somebody comes to you and says it's the firewall, chances are high it's not the firewall. If somebody comes to you and says it's the network, chances are quite high it's not the network. So it's okay to have them give you any kind of idea that they have, but you need to verify yourself. And the one thing that made question? No question, okay. The one thing that made this quite challenging was that I couldn't actually put any kind of software on the systems and capture. So I could not use Wireshark on the client to figure out what the packets are doing, because you cannot install software on medical devices unless you want to risk losing certification for them. Which means they can't be used anymore, and that is a bad idea. So sometimes your scenarios are a bit limited like this, and then you need to figure out a way how to work with this. And let's take a look at what you can do. So I have a couple of virtual machines running, and I hope that this will work as I want it to. So let's say the guy tells me this, let us assume this is the client. It's just an example, Windows 10. And the server is just an example, Windows Servers 2016. Let's assume that this is the client that I cannot install Wireshark on, that I need to work with what I have. What could I do? First of all, he told me the firewall is blocking my things. The firewall is blocking the communication. So what is the first thing that I want to check? Well, is there a firewall in between? How can I do that? Well, first of all, I could check if there's anything in between, right? So if he can tell me what the IP address of the server is, I could just ping it and see what comes back. So that's what I did. Ping 10.1.10.1. And it comes back like this. So is there a firewall in between? It's a little bit small, maybe. Can it be zoomed? Yeah, it can be zoomed. So any firewall in between? What do you think? No, especially not if you know it is a Windows Server 2016. It will have a TTL of 128, and I get back a TTL of 128. I could also do a couple of other things. For example, I could check what is my IP address and what is the IP address of the server. Are they in the same subnet? Yeah, you could go like ipconfig, and then you would see, well, my IP address is 10.1.0.50. That server is in 10.1.10.1. So are they in the same subnet? Well, if you're used to looking at /24 networks, then you say it's not in the same network. But you need to take a look at the net mask as well, which is 255.255.0.0, which means the first 2 bytes or the first 2 octets are the network address. So the network address is 10.1, and the rest is the node octets. So the 2 of them are in the same subnet. It's a big subnet. It's a class B, as we used to call it for in earlier times. Now we would say it's a /16. So those 2 findings would tell me for certain that whatever he's telling me about this thing not working is not because of a firewall, because the 2 systems are in the same subnet. Yeah, so it must be something else. And well, if you can't capture on the system, and usually, to be well, quite honest, you should never capture on a system if you can avoid it, because it's giving you biased results. I will go into that in my other talk about network capture 101. But sometimes you can't even use a span port or a tab because you don't have one, or the span port is not available because the network administrator is not available and you need somebody to configure it for you. So there's one trick recently that you can do on a Windows system if it's Windows 10 or newer, and that is the fact that Windows can capture packets without Wireshark. Yeah. I don't know if anyone has ever tried this. There's something called pktmon that is part of Windows now. And you can use pktmon to capture packets and say pktmon start -- capture pktmon. Okay, I need to cannot obtain current state. It's probably because I'm not in an administrative shell or command line. It started as administrator. Let's go again. Okay, so it should be capturing now. It's capturing into the system32 directory, which is not great. That is actually not a good idea. Stop. Go away. No events lost. Great. Delete pktmon.etl. Let's try this again. Let's go to C traces and do it once more. Okay, starting the capture. And now I would, for example, run an application, and I don't have an application on this because it's just an empty Windows box. So I'm just going to do like a FTP connection to that server. Let's assume that the guy wanted to use FTP, right? So this is what I get. It doesn't work. In this case, I also get a pretty good impression what is going on. Connection closed by remote host. So that is usually the equivalent of the application telling you, hey, I got a reset packet back. But we don't know yet. So let's stop our capture. And now we have something called pktmon.etl. Now this is a format that you, as far as I know, unless the developers have done some magic again, cannot open in Wireshark. So what you need to do is pktmon, and you see down here there's a command called etl to pcap, which means it can convert the ETL file. And now I have a pktmon.pcapng. Yeah, all with a system without running Wireshark or installing anything. It's just the Windows operating system. I installed it yesterday from scratch. It's nothing added. It's just Windows, and I can capture packets. So that's great. Now we need to take a look at this thing. So let's find it. What you usually would do in this case is now plug in a USB device or USB stick, storage device, whatever, and copy this trace file off of the system. I need to stop my presentation for this, I think, because I want to drag and drop it out of the VM. Go. This one over here. So this is the equivalent of using a USB stick and copying it. And now I can open it in Wireshark. Yeah. So it looks a little bit crazy. And that is because I'm using virtual machines. But what we can see here is we have a SYN packet. And let's isolate that real quick. I'm using right mouse button on the SYN packet, conversation filter, TCP. That's still a lot of packets. But in the end, we'll see there's a reset ACK. So this connection gets shut down. And well, something is not working well. It looks like there's no service running on that port, right? Because we get a reset back. This trace is much more confusing than it would be on a real life system, because somehow the virtualization environment adds all these additional packets here. In a normal capture, if you do this on a normal system, it would just be the SYN and the reset packets. Yeah, so we can try that kind of thing. For example, if I use real systems with Wireshark, of course, I'd have to. Okay, well, why don't I see my interfaces? Because I opened this with a trace file. So refresh interfaces. There they are. I don't know if you know this, but if you double click on a pcapng file, it will start Wireshark without doing a list or gathering the list of all the capture interfaces, because that takes time. So double clicking a capture file opens the Wireshark without the interface list being filled. So if you need the interface list to be filled, like I do now, just go to capture and refresh interfaces, and then it will scan for all the capture interfaces again. I have quite a few. Let's say we're using this one, and I want to try with a system that is called host 192.168.124.50. This is a capture filter that I'm running so that we see a little more clearly. No, that's the wrong command prompt. Let's use the other one. So let's say I want to do FTP to 192.168.124.50. Connection refused. Why doesn't it show any packets? Interesting. Did something wrong here, I think. It was on this one, host. That should have worked. Why didn't it? Let's try again. Because I have a display filter in there. That doesn't make any sense. Okay. Now again. So this is how it would look like, right? If you're doing that on a real system, not a virtual system, you get SYN reset, SYN reset, SYN reset. So, yeah, more than 3 times, but you get the idea. So basically, this tells you this service is not running on that port. There's no FTP service running. Okay, and this is something you can do really easily, and which means in this case, I went to the guy and told him, well, first of all, there's no firewall. Second of all, your service isn't running. And remember, this was a ransomware case. They were restarting tons of servers, working on them all the time, like 24/7, and somebody just forgot to start the application. It just wasn't running on that server at that time. But they were looking at the client side and they saw we cannot connect. And the idea was, yeah, I know that we put in a firewall because of the situation being hacked. They wanted to improve security. They added a new firewall in the middle of the network to filter traffic through all the subnets. And of course, since they all knew that, they all blamed the firewall all the time because it was the new thing in the network. They just had forgotten to start their application. Yeah. So this was like, it took me 15 minutes to troubleshoot this, but I've seen people getting stuck with a situation like this for a day or two until they figure it out. So this is really easy to do. And well, let's take a look how it looks like if we start the server. Hey, so start the server. So now if I'm getting in there, still not working. But why? So first of all, let's check if the service is running. How do I check if a service is running? And I need to change the colors because I think you cannot see it well. Screen text black, screen background white. Okay. So how do I check if a service is running on port 21? There's another useful command many people don't know. It's called netstat. And it will list all the ports in the system that are being listened on. Oh, this takes quite some time. Okay, somehow my server is not running. Or I'm not getting the right output. Let's try -in. Okay, I used netstat -an or -in, and you can see, well, it's in listening state. Yeah, I should have shown you the same thing before I started the FTP server. It would not be there. But netstat -in can give you the list of services that are running, and you're looking for the addresses and ports with a listening state. So now I know the FTP server is running, but still I can't get a connection. What's going on? So the question would be, is there something different now? Okay, let's do this again. And can stop this one. Close it. And start my pkdaemon again. Or let's do it in an easier way. Let's say we are allowed to install Wireshark on the server, because you all have seen how pkdaemon works now. So instead of doing that on the client, I'm now using Wireshark on the server. And let's say I want to see what's going on port 21. Leave that running, go back to my client. Where's my FTP command? There it is. All right, let's see if we got something. We got something. Okay, so turn off the colors because they drive me nuts. And increase the size of the packets. So what do we see here now? this is not the same as before. It's not SYN reset, SYN reset. So the service is actually running. Why? Because we have a full three-way handshake, right? Yeah, so we have the SYN, we have the SYN ACK, go away, and we have the ACK. So the connection is established, and what happens next? In the next packet, the server tells the client, by the way, I'm done. It's like, huh? Why? I haven't even had a chance to tell you what I want from you. Yeah, so this is kind of irritating. And it does it really quickly. I don't know if you've ever looked at the delta time. This is the relative time here. Usually it's quite useful to change the time column to the delta time, so the time between packets, but we don't need to do this in this situation. Well, we can do this. Let's say we're doing that in time seconds since previous displayed packet. So it took the server to tear down the connection after the handshake was complete 641 microseconds. That is like instant. It's like, I don't like you, or I don't want to talk to you, or something like this. So first of all, is this a network problem? So is the network not working correctly? Who thinks the network is at fault here? All right, nobody. Who thinks it's a server software problem? A few. And the rest is still too afraid to raise their hands, but that's fine. You don't have to. Oh, we have a lot more on the virtual participant side. Very good. Thank you, gentlemen and ladies. Ladies and gentlemen, sorry, that way around. So yes, this is a application problem. So what kind of application problem could this be? Well, what I would do is take a look at the application and see what's going on. Maybe I can find something. And well, if I'm looking at this server, there's a listener. It listens on various IP addresses, protocol settings, FTP and TLS, rights management, a lot of things here. But if we look closely enough, there's something called filters, and there's a disallowed IP range, which means clients from that IP range are not allowed to connect to the server. Well, in this case, I added it, of course, to show this to you. Normally, you would not do this and exclude the clients that you want to be able to connect. You would exclude all those who are really not allowed to connect, or you would allow all the ones that you want to connect. So if I remove this setting, telling the server accept anything from anywhere, we will see that finally, yay, I can log in. Empty password. Not a very good thing to do, but it's a demo environment, so sue me. Okay, the capture was still running, I think. Yes, you can always ask a question.
Why was the three-way handshake allowed to proceed when that subnet was excluded in the setting?
Okay, so the question from Tony is, why was that three-way handshake allowed to complete if the IP address was excluded? That is a very good question, because we would assume that why not just SYN reset the whole thing? And the answer is because it's an application setting, and you have to think about the whole involved parties to be operating system with a network stack, with the application sitting on top of it. So the SYN ACK is handled by the TCP stack, not the application. And the application only gets notified that there's somebody wanting to talk to this FTP application when the handshake is complete. So the operating system handles the three-way handshake. When it finishes, it tells the FTP server application, hey, I got a new client for you. By the way, the IP address is 10.1.0.50. Then the application looks in his allow list or filter list and says, I don't like him, and shuts down the connection. So the reason why the handshake completes is because the application at that point in time doesn't already know that there's a connection request coming in. This is why it looks like this. And it's a very common thing. If you ever see something like this, and then the server, even though it accepted the connection, tearing it down right away, that is almost always some sort of filtering on the application side, which says this one is not allowed in here. Yeah, so keep in mind, handshake performed by the TCP stack, like part of the operating system. The application sits on top of it. It only gets notified as soon as there's a working new connection established, which means after the handshake, and then it can react to it, not before.
Sometimes you see those problems also with load balancers.
Yes.
So they will accept the connection and then they look to see if there's anyone available.
Yeah. Yeah. So a remark from the back here is that it also happens sometimes with load balancers. If you're not familiar with load balancers, those are systems that take the initial connections from the clients, and then they try to find out, is there any kind of server in my background that can handle the request? Usually you have like a couple of servers that are all available or more or less available, and then one of them gets the request and then answers, and then the proxy replies. But if it the load balancer replies, but if it can't get any server because there's none, yeah, well, then you see the same thing. Yeah, so knowing what is in your network is always helpful, because if you know, oh, this is a load balancer and it's telling me this kind of thing, then you have an idea. Maybe it's because the pool of available servers in the background is just empty. Okay, so these are a few things that can go wrong, but as we saw, none of this is a network problem. But people will blame it on the network, of course. They will blame it on the firewall, they will blame it on whatever, but in this case, it's just a server problem. All right, so let's put this away. I think this can go down too. So it's not an evil firewall because there was no firewall, right? Okay. So the conclusions are: verify the problem description, because they sometimes tell you things that are not true. You don't always need Wireshark or packets to troubleshoot, because you can use other means at first. Know your command line tools, the capabilities and limitations, of course. A ping, and that is the common thing to say at this case, in this situation. If ping works, that doesn't mean that much, right? If you can ping a system on the other end of the network, it basically means this IP is in use by something. It doesn't mean it is the server that you actually think it is. It doesn't mean that there's an application running on that thing. It doesn't mean that the TCP connection will not be in trouble when it gets established. Ping basically means, yeah, there's a route from me to this IP address, and that works. Okay, so the tools are ping, traceroute, and netstat, or SS. SS is the thing that you would use on Linux systems these days. They used to use netstat as well, but it got replaced by SS, probably because they're lazy and don't want to type that many characters. So, well, SS it is. And now we look at communication breakdowns. How much time do I have left, Chris? Do you know? 9 minutes. Okay. Communication breakdowns. Well, what can happen? Well, I can have this established connection. So let's say we're already sending data. It gets acknowledged. I send some more data. And suddenly the server says reset. Well, let's assume there's more data to be sent, but in the middle of nowhere, we get a reset. And that could be a TCP application problem. For example, if the application crashes, what does that mean? Well, the port is released. So the operating system knows, oh, there's nothing running on this port anymore, but I have an open connection that tries to talk to this port, and then it will send a reset packet. Yeah. once again, we need to be a little bit careful here because normally a nice way to shut down a connection would be a fin-ACK sequence, like a four-way handshake saying goodbye. But since a couple of years, a lot of applications also use reset to get the communication terminated really quickly because it releases resources a lot faster. So we need to be actually sure that there's more data that needed to be sent, but we see a reset to diagnose, hey, this is like a crash of an application, or maybe there's something in the TCP data that is so badly wrong arriving on the other side that the server decided, hey, I can't work like this. Let's stop and shut it down. The next thing would be data being sent. Come on, nothing happens. You want to have an acknowledge back, right? The server needs to acknowledge your data at some point, but it doesn't. And then this client is like, okay, I've waited for a minute. I'm giving up, sending a reset. Yeah, and we can take a look at an example like this. Once again, I need to. I think it was this one. So there's a couple of connections in here. Let's see what we have. I think this one is the interesting one. Since an ACK, everything's fine, protocol exchange, blah, 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 blah. Some retransmissions, and suddenly, a reset packet. What's interesting about this trace, if you take a look at it? Well, it used to be going back and forth, like packets being exchanged, acknowledged, sending data. But for the, well, I don't know how much time it is in the end, but from packet 80, from this one, and let's say a time reference here to get an idea how long it takes, all the way down here, there's only communication from 192, 168, 124, and 100, and the other side doesn't say anything anymore. It's just quiet. So let's see, how long does it take for the client to use patience? And I have the reference point up here and my relative time down here. So you can read it in this column. Get it a little bit more exposed. How long did it take until the client finally gave up? 24 seconds. So for 24 seconds, it tried to deliver data and heard nothing back. And well, 24 seconds is like infinity in network communication. It's way too long. So something happened on the server side. We don't know exactly what, but we can say, yeah, the client was losing patience, and rightfully so, because this is not going to work anymore. Yeah, this is a typical reset situation where it is used to terminate a session that is not going to be successful. Yeah, it's a typical example. Very often, if you see something like this, you see that one side is sending, nothing is coming back, and losing patience and resetting things. Why doesn't the client retransmit? Because it is still allowed to, it is retransmitting a few things, but it's probably because it's still allowed to send more data because of the window size. The window size in TCP specifies how much data can a client send before it needs an acknowledgement. So it probably sent all the data that it could in the packet that it sent. Let's see, maybe we can check it out. Let's see how much bytes in flight 936. I have no idea how big the window size is from the other guy. It's much bigger. So it could even continue to send more, but maybe it ran out of data that it needed to send. And then it just waited for an acknowledgement. Yeah. So there is no reason to retransmit if you're not hearing anything back. And that is, well, one of the things that is really sometimes hurting connections. If you're sending packets and you're not getting anything back, you don't know what happened. And you can start trying to retransmit, which is what the client is doing here every once in a while. But the only sure way to know that there's been packet loss if you get an acknowledgement back telling you, hey, I got this many bytes, but there's something missing. We don't get anything. So he's just sending without any kind of feedback and doesn't know what to do. Okay, so let's take a look at the remaining connection breakdown things. Since SYNAC, everything's fine. And then a reset, or maybe a FINAC. So this is something that we used, that we already saw as an example. Yeah, it's an application-based IP ban usually, or a load balancer being in trouble. And the last one could be this one. That is, you don't see this very often. It's, for example, if a firewall has a network intrusion detection system and it detects an attack pattern in the data, then it tries to shut down the connection. And it does it by sending a reset to all parties involved. So basically, firewall spoofs or invents reset packets that look like they're from the client to the server or from the server to the client. So it sends it both ways, and you see a reset packet taking down the connection. This is very often 2 minutes. I'm almost through. This is very often something that you see in something like this. So we only see it one-sided in this case. I think if we take a look at the TTL, the 10.0.0.10 has a TTL of, where is it, 126. We can pull it up here to put it into a column so that we can see it. The server, or this IP 10.0.0.10 uses 126, so it's 2 hops away, probably, most likely. And the reset coming in suddenly has a 255. From the same IP address, now a TTL that is very different. It's much higher. It is only 0 hops away, so it must be from my gateway or my firewall. So we can say with relative certainty that this reset is forged, because the server would send his reset. If it would originated from the server, it would also be sent with 126, not with 255. So this is a forged reset. So using TTL can be really useful in situations like this if you want to find out who did send what. If you see a change in TTL, that could be that there's something sending like a man in the middle and spoofing packets. Okay, and I think I'm almost done because we already did the scenario 2. This happens to me a lot, that I jump in my demos, and that means it's time for questions. I don't know if we still have time for questions, but, or if we have any kind of questions. Chris, are there any from? Okay, so no questions from the virtual attendees. Thank you for joining us in here. Anyone here having questions? Nobody. So, okay, I hope this was useful to you and you got a few ideas on how to troubleshoot a little more quickly. You still have one? Okay. Okay, why is it reset ACK and not just reset? Let's see if we can find this one again. Yeah, you can see there's flex here that is saying reset and acknowledge. Well, the acknowledgement usually is set when the application has received data, it was a working connection, and it's still acknowledging the remaining data being sent and tearing down the connection in one go. This is usually a good indicator to see if the reset is coming from a system trying to shut down a connection. I think in this case that the system spoofing this just also set the ACK flag. It's hard to tell why it does this. It would also be achieving its goal just by setting reset, not just the ACK. But the reset ACK, very often you can see that the client, for example, sends reset ACK. Reset ACK in here, it comes with a write TTL. That's because it wants to tear down the connection in a quick way. And that is useful to see, oh, this is a quick connection abort. Okay, so it could be both in this case. The spoof one could have both flags. The important one is the reset one. Okay, so thank you. And as I said, I hope it was useful. If you still have questions, you can find me on Twitter. You can also email me, or you can read my blog. I haven't written in a long time because I had other things to do, but I think I will try to continue in the future. Let's see. All right, thank you.